In this video, what we are going to do today is we're going to review the electromagnetic spectrum, and I'm going to give you a quick rundown of the math problems that we need to do. So everybody should have a sheet of paper that looks like this in front of them. This is the one slide that talked about the electromagnetic spectrum. So you want to have this paper out in front of you, and we're going to label a couple of things. A spectrum, just as a little bit of a reminder, anything that has a spectrum, or when we talk about a spectrum, is going to be a range. So you need to think of the electromagnetic spectrum as a big long range. These are all the options for things that are electromagnetic radiation or that travel as a wave in space. And over here you're going to notice that one of the things that does is this actually gives them a value for the wavelength. And down on this end you have things like radio waves, microwaves, and you'll notice that there is a longer space for a wave. Now when we measure a wave, you go between two repeating points. So for example, you could measure the wavelength from here to here. You also could measure it from here to here. Okay, so it's however long one repetition of a wave is. Now down on this end for wavelength, I want you to put high and up arrow to represent long or higher wavelengths. And down on this end over here, I want you to put a down arrow or a shorter wavelength. Okay, now this is going to come into play when we talk about relationships. Now I know I'm not here today, so do me a favor, the next time you see me, someone ask me to show you the demo with the slinky. Okay, this is a really easy concept when you can see the slinky and show the relationships, but since I'm not there today, we can't do it. So anyway, wavelength, radio is the long end, gamma is the short end. Now if we come down here to frequency, okay, frequency and wavelength are inversely related. So you'll notice her frequency is measured in hertz or 1/seconds. This is the math we're going to do here in a little bit. You'll notice you have the smallest frequency values. So down here next to frequency, I want you to put a down arrow. Okay, a down arrow. Over here, to represent a lower value, over here I want you to put a arrow that says up or higher frequency. Now, the math we're going to do, the first math equation we're going to deal with is going to be wavelength and frequency. The second one is going to pull in energy and frequency. So the other thing that I want you to label on this is over here where we put low frequency, I want you to put an up arrow. Nope, I'm lying. Don't do the up arrow. Do another down arrow over here to represent low energy. Okay, and again, hopefully the slinky demo will help you make a little bit more sense of this. But when you think about low energy, this is where we can kind of equate radiation to danger levels. For example, radio waves. There are radio waves floating around us all the time. They have extremely long wavelengths, almost a kilometer. 10 to the third meters is a kilometer. But they have very low energy, meaning they do not pose much danger to us. On the other side over here, if we go to the other extreme, you have gamma rays that have extremely short wavelengths, 10 to the -12th. That's like a picometer, right? 1 picometer. So if they have very high frequency, these are the guys that are also going to have very high energy. So over here on the end by the high frequency, I want you to write high energy as well. And this makes sense. Gamma rays and X-rays are things that could potentially be dangerous to our cells and that can cause us to potentially get into the DNA and mess up the DNA and cause cells to do things we don't want them to, which is essentially what happens in cancer. So you need to make sure you're comfortable with this relationship, that energy and frequency are directly related, and we'll write this down here in just a second. The other part that you need to label, and you may want to write this down or color this in a little bit later. I know your pictures are in gray, but you need to make sure that you write the order of Roy G. Biv. Okay, I'm going to write it out here too, but you need to know the order, Roy G. Biv. Okay, because these go in a very specific order. Red has the longest wavelength, violet has the shortest wavelength, and the visible portion of the electromagnetic spectrum is very small. Okay, we can't see radio waves, we can't see X-rays and gamma rays. The visible portion is this very, very, very small portion. And again, it goes from Roy G. Biv. So red has the longest wavelength, violet has the shortest. And you will eventually on a test have to be able to rank types of electromagnetic radiation from wavelengths or energies, and the easiest way to remember it, just past red you have infrared, right? You need infrared goggles, and we can see those. And just past violet, you have ultraviolet, and these are the ones from the sun that can kind of do us some damage. So, just a quick recap on the electromagnetic spectrum. Again, somebody ask me about the slinky the next time that I see you, and we'll talk about that one more time. Okay, the other thing I want to do before you guys get started on the math problems is to just really give a quick rundown on the math problems. So, you should also have a little half sheet of paper that has the math problems that you guys are going to work on here. So I want you to take out that half sheet of paper. If you haven't already done so, take out your journals as well, not your lab notebook, because this is where you're going to solve the problems. And up at the top of the half sheet, you'll notice that there are two equations and there is some given information. The first equation mathematically looks at frequency and wavelength. So you have c, which is the speed of light, which I've already given you down here, 3.0 times 10 to the 8th meters per second. Lambda is going to be wavelength measured in meters. V is frequency, which is hertz or 1 over s. And this equation demonstrates the inverse relationship between these two numbers. Okay, they're inversely related. Remember, the higher the frequency, the lower the wavelength, and vice versa. So this is the math behind where that relationship comes from. And then over here you have the second equation. You have E is energy, V is frequency, which is hertz or 1 over s, and H is what's called Planck's constant, which is 6.626 times 10 to the negative 34th. I can tell you right now that all of this information up here that I'm highlighting, the equations and these constants, these will always be given to you. Okay, so you'll notice they're written on the top of the half sheet, but these will always be given to you. Okay, so in terms of plugging and chugging, you just have to be able to figure out. And the way that you figure out which one you use is based on what they tell you. Okay, so what I'm going to do is go ahead and we're going to do number one together, and the sub will actually give you the answers to the rest of them so that you can check to see that you're on the right track. Obviously, the next time I come in, if you have any questions, we'll get those addressed, but honestly, most people find this pretty simple at this point in the year. So let's do the first one together, model what we have to do, and then you'll get some time to work together to be able to solve these. So if we look at number one, oh, and hold on, if I come back up here for 1 second, this demonstrates an inverse relationship. This one over here, this demonstrates the direct relationship between energy and frequency, and that if energy is high, frequency is high, and vice versa. Okay, again, gamma rays have very high frequency, very high energy. All right, so let's look at number one again. All right, number one, what do they tell me? Yes, we still have to do known and unknown. I will mark you wrong if you don't do it on a test or a quiz. What the problem tells me is that I have a wavelength, for my particular substance that has a wavelength of 590 nanometers. What I'm trying to solve for is the frequency of that wave. So right off the bat, from what they tell me, I have wavelength and I have frequency. Okay, I'm using this equation right here. No mention of energy. I don't even have to touch the other one. But I can't do this yet because wavelength is typically in meters. So the first thing that I do have to do is go from 590 nanometers to meters. I do that by dividing it by 10 to the 9th, setting up my conversion, so that my wavelength is now going to be 5.9, only two significant figures here, so 5.9 times 10 to the negative 7th meters. And now I'm ready to plug and chug. I don't have to keep listing speed of light and Planck's constant is known. We also, when you're doing significant figures, don't ever use the constants. We always use our data. So if I come on over here, I have to write the equation. Don't forget to write the equation on this one. Again, my speed of light is 3.0 times 10 to the 8th. My wavelength, 5.9 times 10 to the negative 7th. Okay, V is my frequency that I'm solving for, so I have to divide both sides by 5.9 times 10 to the negative 7th. Don't forget, when you are dividing and using things with exponents on your calculators, you have to use parentheses. So you want to make sure you can get the right answer. When I solve for it on my calculator, I should get 5.1 times 10 to the 14th. And the unit on this is either hertz or 1 over s. It does not matter to me. It's either exchangeable for either one of those. Okay, so you now have some math problems and study guide and some other things to work on for the rest of the block. Please be good. Usually you are, and I will see you next time to clear up any questions, and then we will go from there. Okay, I hope that was helpful.